5 cents might not seem like much, but when it's 5 cents for every cow every day, then it really adds up. New AminoSure XM precision-release methionine provides the optimal combination of cost, feed stability, rumen stability, and intestinal release to deliver the best cost per unit of available methionine on the market today. Learn how at balchemanh.com/findyourx.
Hello, everyone, and welcome to the Real Science Lecture Series. My name is Scott Sorrell, the Director of Global Marketing here at Balchem. Today, we welcome back Dr. Mike Van Amburgh from Cornell University to explain how amino acid nutrition plays a role in maximizing milk components. Dr. Van Amburgh is a professor in the Department of Animal Science and a Stephen H. Weiss Presidential Fellow at Cornell University, where he has a dual appointment in teaching and research. His undergraduate degree is from The Ohio State University, and his PhD is from Cornell University. He teaches multiple courses and leads the Cornell Dairy Fellows Program, advises approximately 50 undergraduate students, and is the advisor for the Cornell University Dairy Science Club. Mike currently leads the development of the Cornell Net Carbohydrate and Protein System, also known as the CNCPS or CPM Dairy, a nutrition evaluation and formulation model used worldwide. Through the modeling efforts, he focuses on enhancing the efficiency of nutrient use by ruminants to improve the environmental impact of animal food production. So with that, Mike, welcome back.
Okay, folks. So what I'm going to do is I'm going to talk about milk components. I'm going to do it by integrating what I do. I think we should all be doing is energy and amino acids as part of that process. I'm going to recognize my co-author here, Alex Benoit, who's helped me with some of these slides and is a current PhD student in our program. So my introduction here, you know, and I do this now. The world wants cows to be more efficient. There's a lot of pressure to reduce methane and carbon emissions, and I think you know, one of the things that seems common sense but doesn't get talked about enough is that feed efficiency and carbon intensity are directly correlated. Any increase in feed efficiency reduces the carbon intensity, right? And I think anything that we do moving forward, our whole objective, and this is not new, right? This is as old as feeding cows, but we want to figure out how to partition as many nutrients from that feed to the mammary gland as possible per unit of feed intake. And I think you know, we've moved a long ways. Cows are continuing to improve. I'm going to talk about that. Our nutrition is improving, but I think sometimes we have to think a little bit differently to figure out how to do this, right? And I'll talk through that. Essential amino acids are required for protein synthesis, nutrient signaling, and conversion to other metabolites like non-essential amino acids, enzymes, and hormones. The point is that I think there's a lot of work done out there where we talk about amino acids and the whole focus is milk protein. And I think that's misplaced. Amino acids are needed for lots of functions within a cow. And I think we don't have time to go over all this today, but I'll give you a little bit of some essence of this about where amino acids fit into milk components like milk fat, right? Because I think it's important that we recognize that carbon from amino acids can go lots of different directions. I also want to recognize that the system's constantly running, right? And I've got a slide on this that Alex helped me put together. You know, the mammary gland is going to run. It's like any other machine. It wants to make milk, but it can only make milk as efficiently as the precursors that allow for the formation of the protein, the fat, and the lactose, right? And I think about this just like we used to talk about energy spilling in a bacteria, right? If there's carbohydrate available to that bacteria, but there's not enough nitrogen to make more bacteria to use that carbohydrate efficiently, they're going to spill that energy. I think the mammary gland does the same thing. I think the cow does the same thing, in its own way, right? But we don't talk about it that way. That's part of that efficiency that I spoke of. And then there's this obligate requirement for amino acids and fatty acid synthesis. And all of this is integrated, in liver and mammary metabolism, but is not well described or discussed, right? And I'm going to do a little bit today to kind of bring that to light. So again, this is going to be about components, but it's important to appreciate the interaction between amino acids and fatty acids in enhancing milk components. I think that, cows have fatty acid requirements similar to amino acid requirements. It's not quite as discrete, and we've not really identified it yet. But as we get closer to certain relationships on particular fatty acids, we see enhancements in productivity, which suggest, at least from an energetic perspective, putting the right fatty acid profile together and feeding it at the right amount. And I think the right amount thing is important, not overfeeding it is important, that we can find some synergies there and get more milk components. Yeah, and this aspect of nutrition is rarely, if ever, discussed. Yeah, we've got some observations here, and I'll share some of that. And sometimes we also have to think about we have to consider the right precursors for milk fat yield. We focus a lot on acetate, and there's been lots and lots of discussion about acetate. Kevin Harbatine especially has really good data on acetate and done acetate infusions and looked at the potential for increasing milk fat. But I'm going to come back and say I think we also have to think about butyrate in this process, right? And I'll share some of that with you. Where I want to go here and is to talk, and this is because it seems like a left-hand turn here all of a sudden. Why don't I have a genetic slide up here? Well, I was invited. I get invited to go give some talks in places, and sometimes the talks are a little bit interesting, and they cause me to learn and to think differently. So I appreciate these opportunities. One of them was somebody asked me about high-producing cows and what the potential is for high-producing cows in the U.S. and in Europe, in the world, and so you go look at where we're at with our genetic capacity. For milk yield, and you can see here, the upper bounds genetically, and this was John Coles published this in 2010, it was about 35,000 kilos, and the lower bounds was about 11,000. So you're talking about 24,000 pounds on the bottom end, and you're talking about 73 to 74,000 pounds on the upper end. And if you pay attention to world record holders, we've had a few cows, a handful of cows that have been pushing this boundary or exceeded this boundary, which means the genetic potential is actually higher, right? Mathematically, it's twice as high as what their phenotypic expression was. So there's a lot of potential for cows to make a lot of milk out there. And I see this, right? So, and John Cole and Chad Deckow have put out some data, and they would suggest, the genetic capacity is about 75,000. But I live in Cayuga County, New York, and I have cows in the neighborhood that are peaking, between 186 and 214 pounds. That's not unique, right? There's cows in the Midwest that do this. But when you stop and think about what that means, those cows are greater than 44,000 pounds of milk per lactation. They're not the 75,000 yet, but there's cows in herds that are, 40 to 52, 53,000 pounds of milk routinely in commercial herds. And I think we don't see these cows all the time. I do because they're my neighbors, but it reminds me that we have a lot of potential in these cows. We just have to figure out how to tell the cows it's okay to use it. Because I think there's a lot of cows out there that can do this. And, it's the simple questions. It's not simple questions, but, it leads to the question of what are we doing and when that either tells the cow it's okay to do this or detracts from that ability. And when is it communicated to the animal, right? Is it, we know that there's some fetal development that's important. We know there's some early life nutrition that's important, but sometimes, when during the lactation phase, is it okay to tell them to do this? And a couple years ago, when we had the federal order hearings, I was invited in to testify about, my job as the biologist was to help all the processors all the people that are going to rewrite the federal order for payment, how cows are going to change over time, right? So I went to the webpage, this dairy cattle breeding webpage. DECAL had published this, and here's the U.S. sire breeding value for fat from 1957 to 2021. And it's important to recognize that these numbers are a function of the year they were summarized, right? So it doesn't mean in 1957 that all the cows or all the bulls were minus 300. It just means in today's genetic base, they're now minus 300 pounds, and current genetic base is about 150. Well, what's important about this is the change, right? It took us a long time to get to zero. All right, and we crossed the zero line at 2013 based on this 2021 data. But since that time, right, we've gone at almost an exponential rate on the change in capacity for milk fat synthesis or milk fat yield, right? And I found this fascinating. I hadn't looked at it. Hats off to the guys who created genomics, because this is the effect of genomic selection, shorter generation intervals, and all that kind of stuff. The only way to speed this up at this point is to do IVF and really shorten your generation interval. But what I found interesting is that these cows are changing, right? Took 56 years to get to zero, took 9 years to go half that distance. That's a 6 times faster rate of change. What this tells me is that compared to 20 years ago, every calf born today is worth 6 years of genetic selection by comparison, right? Because we have shorter generation intervals. We don't hold on to bulls 5 years until they have a proof and then grow old, making semen. We turn them over fast. So it's a completely different game. What this tells me, and the world is using the same genetic pool, right? For the most part, if you're using AI semen, everybody's going the same direction, right? So the potential to make components is incredibly high in today's Holsteins. Jersey's not moving quite as fast, but they are gaining speed. If you look at the protein side of that, it's the same thing, right? And you go back, my slide's a little off there. If you go back, to 1970, that's where this base was from, and look at the change again. You're crossing the line about 2013. Not quite as rapid rate of change on protein, but still very similar to fat. And again, if you think about it, it's still almost a 5 times faster rate of change due to genomics than it was prior to that. Quantitative genetics was good, but it was slow by comparison, right? Again, this means that we have cows out there that have tremendous capacity for milk protein yield. And I'm not sure that we're consistently seeing that. And I think that's one of our opportunities moving ahead. And I'll give you some examples of that, right? So that makes me think about pigs, right? If anybody's ever formulated a diet for a pig, they use the ideal protein concept. In their swine requirements, they have lysine as a function of energy. So it's grams of digestible lysine per mcal of DE, and all the other essential amino acids are a function of the lysine. So it's all fixed, right? And as they get higher growth potential pigs, they will redefine the genotype and they'll add in a little bit more lysine, right? Which means all the other important amino acids will follow. And they do it also by stage of growth, right? And we in cows still argue about crude protein some days, right? Or we argue about metabolizable protein. We're way behind. But I think the more interesting thing is if cows were pigs, we'd have a new genotype, or maybe 2 new genotypes since the onset of in the application, kind of universal application of genomic selection. So I think, if you want to use this as our analogy, we probably have a new genotype or 2 of cows out there, and we don't really know what their requirements are to produce all of that fat and protein. So I think that's our opportunity. I do think the cow is the innovation today, And we need to spend some more time kind of reassessing what she can do and what she's capable of. And I'll give some examples of that towards the end of the talk. All right. So back to the idea of integration. I've used this a lot. Gerald Lobley was a brilliant scientist, and just before he retired, he was invited to give a talk at the EAAP meetings or the physiology meetings. I can't remember which one it was. It was in 2007 in France. And he had this paper he called horizontal integration, right, or horizontal aspects. But he made this statement, and I think it's really powerful. It says, although it's been traditional to consider protein and energy metabolism as separate entities in mammalian metabolism, most scientists recognize this as artificial, that they should be considered together, because that's how nutrients are ingested and utilized, right? And he went ahead and quoted evolution. I don't think I'd ever do that, but good for him. But the idea here is that he made a really strong point, quite a few years ago, that we needed to start to think differently. And again, I don't have time to go through all these slides today. I took some out, but one of the things that he did is he took a couple studies where he followed, they labeled the carbon from the amino acids and followed the carbon through the cow. And they found amino acid carbon in the protein, obviously. They found amino acid carbon in the lactose, and they found amino acid carbon in the fat. All right. So the idea that amino acids go in and they go, uniformly to milk protein, or they go uniformly to some location in a linear way is completely incorrect. It's going to go in multiple directions, and we need to understand this and appreciate it, because it's probably part of how we get better component yield in cows because of the obligate requirements for these nutrients. And Alex kind of put this together, and this is probably the right time to bring this in, because I think this is kind of how, from an assembly line perspective of building milk components, I think this is a good analogy, because you can turn the machine on and the machine can run, and if the widget is, if this box is going to be milk fat or milk protein or milk lactose, but any of these precursors like amino acids, ATP, other carbon sources, reducing equivalents, or glucose are not available at any one time, the machine doesn't stop running. It just doesn't run as efficiently, right? So this is my version of energy spilling in the mammary gland, where it's going to keep running. It's going to make as much product as it possibly can, given the resources available to it. But if we can figure out how to provide the right profile of these precursors in the right sequence, in the right profile, and do it all together, maybe we can make this thing much more efficient, because we're making something at every turn, right? So we're using the energy much more efficiently. And this is how, I think this is how I visualize cows making components, right? How efficiently can we keep this machine running, right? Part of that is regulated, right? And we know this. There's lots of regulation here. I'm going to use one slide. This is mTOR. And I think there's some interesting things about this regulatory function. mTOR has been talked about a lot, right? But if you come in at the top and you're talking about major things that drive the initial function, well, it's all energy, right? And the one I'm going to focus on here is insulin. Insulin's going to, but you could do growth hormone, you could do prolactin. There's a bunch of other things we could throw in there, but I'm going to talk about insulin. So insulin is going to, the more propionate we make, the more propionate is converted to glucose, the higher the insulin signal, the higher the insulin concentrations, or the greater the insulin production. Maybe not the concentrations, but the production. And a long conversation with Lance Baumgart about how much insulin does a cow need, and how high should the concentration be. And he says they don't need any. And I said, well, they do need some. I think it depends on when and where and how much it's cleared and where it's cleared and things like that, right? So, but there needs to be some in there to be able to send these signals to stimulate mTOR function, so we can get more component growth. Because if everything is set up right, well, now we're going to go through the cascade, and if we have the right substrates, maybe we'll get relocation of our SREBP1, the translocation, and now we can get some more lipid synthesis, or we can stimulate some more cell growth, or we can stimulate some more protein synthesis and lactose and get greater lactation output, right? There's ways to interfere with it, right? Do you have the right amino acid profile? Do you have the right substrates to stimulate the lipid enzymes, fatty acid synthase, steryl-CoA desaturase, acetyl-CoA carboxylase, right? You could stimulate it up here with insulin. What's really fascinating about that is we can stimulate it up here with insulin, but if we're short on the amino acids, we're going to short circuit some of this signaling. If we're short on some of the fatty acids and or amino acids necessary for these enzymes, that's going to limit the amount of lipid synthesis, right? And I'm going to talk about that because I think sometimes we get focused up here and we don't really know how to integrate the rest of this. But I think what's going to be interesting to you is this aspect over here about lipid synthesis is most likely amino acid sensitive, right? So if we look at some of the old literature, Mackel, Bainaz, Lee, and this is a study from Tim Mackel where they infuse water, casein, water plus insulin, casein plus insulin. You look at dry matter intake, not remarkably different. Milk yield, so it's slightly changed. But as we infuse the little casein, doesn't really do much, but you add some insulin with just water, and you see a significant change in milk protein output. And then you add a little bit of casein, and you see a little bit more of an increase in milk protein percentage and yield, right? So this is the idea that insulin's driving the reaction. If you want to drive it, if you want to use mTOR as your regulatory function, that's fine. That's kind of probably what's happening. And when you add some of the amino acids, you get just a little bit more push, probably a little underpowered here to make that significant given the number of cows in these clamps, but you get the idea that we're moving up as we add both insulin and protein, right? But there's insulin-induced genes, SREBP1 and acetyl-CoA carboxylase, fatty acid synthase, and all of those, right? Well, that comes back to, so then we come back to the amino acids and we say, okay, we've got all these regulatory functions and we've got insulin. What about the amino acids, right? And Mepham published this in 1982. So you did the group 1, group 2, and group 3 amino acids. And Helene has talked about this a lot. And Helene and I used to have these great conversations about how cows were disposing of amino acids, but she would always get focused on lysine here that's in the group 2s, right? And it takes it up greater, it's more taken up than comes out in the milk. And the same thing here in terms of efficiency, the same thing with the group 3s, right? It goes the other direction. Well, this is really interesting, right? But she would say to me, Mike, why does the mammary gland take up all the lysine it sees, right? If it's an essential amino acid and a limiting amino acid. And I would look at her and say, well, there must be a requirement there, Helene, that we don't fully understand because it's not all going in the milk protein. I says, but we haven't really identified all those requirements, right? And and she talks about, and she was fixated on this for good reasons, and she wrote a couple papers about it. And she says, well, lysine undergoes obligate catabolism in the mammary gland, supplies nitrogen for non-essential amino acids, and the level of catabolism can shift in accordance with the non-essential amino acid supply. And I think this is a really interesting point because we forget that the essentials can get converted to non-essentials. And we talk about the non-essentials as if they're not required, but I will argue strongly that the non-essentials are required. And when they're not available to fill certain pathways, the essentials will convert to fill those pathways, but that lowers the efficiency of use of the essential amino acid. And I think that is confusing because we think we want to use these with a higher efficiency because that's how we're going to make everything work better. right? So I think there's been some confusion about what kind of an efficiency should we see for these essentials. And if we don't see it in milk protein, does that mean it wasn't effectively used? And the answer is no. All right, so let's play off of this a little bit. So I'm going to play on the lysine thing because I think this is interesting. This paper was published a few years ago by Lee. They're using primary cells. They're incubating primary mammary cells, bovine mammary cells, and they did a series of incubations. So this is the effect of lysine on milk fat synthesis in the absence of fatty acids. I think this is fascinating, and they're looking at relative SREBP1 protein levels, right? So these, SRBP1 is going to be important for stimulating the synthesis of more milk fat, and you can see, a significant difference in the expression of SREBP1 as you titrate in lysine. Right, and you can overdo it, and we know that, and you can see that here. And in this particular system, 0.7 millimolars was what was ideal to get the largest increase in SRBP1. But if you move over to lipid droplet density per cell, all of a sudden you see that the same kind of thing that we're actually seeing an increase in lipid droplet formation as you see the change in SREBP1. Well, this is fascinating because this is suggesting that lysine is inducing, right, this whole cascade. Well, that's interesting, right? That lysine, an essential amino acid, is involved in inducing fatty acid synthesis, right? Okay. So what happens if we add fatty acids to this, right? So they repeated it, and they looked again at SREBP1 levels, and you see this really significant increase at the 0.7 level, and higher increase, a greater increase in the presence of the fatty acids. And the fatty acids were oleic and palm. Okay, that sounds pretty interesting because we've heard a lot about that. Adam Locke talks about that a lot. Harbatine and a few others have done the same. Look at secretion of triglycerides, significant effect of lysine with the fatty acids. Look at lipid droplet density, and you see the same kind of thing. And what's interesting is when the fatty acids are included with the lysine, if you look in the previous data or the previous slide, let me see if I can go up. Yeah, you see a significant drop, right? Even though they're still different, you see a significant drop as the lysine concentration went up in the absence of the fatty acids. When you add the fatty acids, you still see a numerical decrease, but statistically it's not different. And finally, you get to a significant difference here. So again, there's a synergy when you have the lysine and the fatty acids available to the cells, right? Suggesting that they're going to be more efficient with a certain amount of lysine and a certain amount of oleic and palm in the system. And then if you put it all together one more time and you look at, they've got 0 is no treatment, lysine at 0.7 millimole, fatty acids at 50 micromoles of palm and 50 micromoles of oleic, and then L plus F is the lysine and the fatty acids. And it's a fascinating thing. If you look at the SREP1, boy, you see a nice titration there. There's lysine, there's the fatty acids, there's a combination. FABP5, right? Some other protein sources, right? Doesn't really matter here. Any of them work. Secretion of the triglycerides steps it right up. That's cool as all get out, right? And the same with the lipid droplet densities. Right? Add some lysine, get a significant change. Add some fatty acids, get a significant change. Put them together, and you get a synergy there, right? So again, lysine, right? Amino acids involved in the initiation of fatty acid synthesis. Okay, so obviously you're not going to see that as an increase in the efficiency of use of lysine directly, because it's not coming out in the milk protein, right? There's no net effect. But the cool thing is that it's initiating the response, so we're going to get more energy corrected milk. And I think this is the fun thing about it is, again, the gland wants to do this, but if we don't, back to that conveyor belt, if we don't put everything together correctly, then we're not going to see this efficiency. Okay. And that's what these cells are telling us, right? We still don't know exactly what that is in empirically when we feed the cow, but we're working on it, right? That's our opportunity. And then if you inhibit one more here, if you inhibit the lysine stimulated expression, there's definitely a big effect here, just to prove that this is real, and you can take it away if you inhibit some of the downstream or some of the upstream and downstream expression. Okay. So using bovine mammary epithelial cells, lysine-induced fatty acid dependent SREBP1 expression. SREBP1 is a key regulator of fatty acid synthesis in the mammary gland and is also sensitive to insulin. This was done through G protein coupled activity, which induces PI3K and AKT. You guys can read all that, and also done through fatty acid binding protein 5, which also regulates lipid metabolism. So there's this whole cascade of things going on around mTOR, where lysine as an amino acid is not stimulating it directly, it's stimulating it indirectly through the expression of all of these enzymes and the upregulation of these enzymes around fatty acid synthesis. So again, pretty cool stuff. One of the reasons we got to make sure we feed enough lysine if we're going to feed methionine. Okay, and wouldn't you know it, I'm preparing slides and I find this lit review looking at the effects of feeding rumen-produced lysine during postpartum period and performance and amino acid profile in cows. And I think this is interesting. Lysine is a percent of MP, so they're going back to the traditional way of looking at this, 6.5 versus 8.5. And it's not significant. Well, you do see a significant increase in energy corrected milk to the current comment. You see a trend for milk fat. You see a significant difference in milk fat yield. You see significant increase in milk protein percent and a trend for milk protein yield. I think this is interesting, right? Because if you look at this and you look at the proportion, you got a greater increase in milk fat than you did in milk protein out of this meta-analysis. And I think that to me is intriguing and kind of supports what I just showed you, in that when we put the right amount of lysine in there, get it to the mammary gland, but also you give it the right amount of fatty acids, we get a nice increase in milk fat. We may also get a concomitant increase in the milk protein, right? So just to tie that all together. And they gave some nice graphs. Again, here's the adjusted milk fat yield and metabolizable lysine as a percent of MP. And you see a pretty, here's your line. And if you look over here at adjusted milk protein yield and metabolizable protein, lysine as a percent of metabolizable protein, you see the same kind of effect. But notice where the steeper line is. The greater effect is actually on milk fat, consistent with that data that I showed you from the Lee study. Okay, so lysine, we want to tie this together with de novo, right? And again, we're at the point in the industry, due to the work of people like Dave Barbano, that now we can start to disassemble the milk fat and look at de novo mixed and preforms. So when we look at the Lee paper again, and you really pull it apart, the de novos were the ones that were really increased, right? And we know that MET and leucine also increases their expression of SREBP1. It's again from the same paper, but there's some other papers that show that arginine also increases de novo and mixed fatty acid synthesis and expression of those enzymes, right? So again, it's not all on lysine. We've got methionine, we've got leucine, and we've got arginine tied in there on the fatty acid synthesis side. So I think if we want to think about energy corrected milk or milk fat, we got to remember that the amino acids are really essential to that whole thing. Again, more of this. I think in the interest of time, I'm going to keep moving, but the idea, I think you guys have got it. Oh, this one's kind of cool. Fatty acid synthetase expression was decreased in histidine and lysine deficient human liver cell medium. Again, the pathways are all the same. The biochemistry is all the same. When they added the histidine and the lysine back, the process was reversible. So in other words, fatty acid synthetase expression is amino acid dependent. So if we're thinking about milk fat yield, milk fat concentration, amino acids are going to be essential in that process. And here we can implicate histidine just as well as we can some of the other amino acids, right? So in the integration, right, many of you have heard this. We came up with this approach a few years ago. We are working to get version 7 out. It is in process. It is out of the house. How's that? It's not here. It's in the hands of others. It'll take them a little while to get through the whole process, but we've integrated the amino acids on a gram per mcal basis, and many of you have seen this stuff. It looks like prior information. I'm gonna keep moving fast through here because it gives us the ability to do that. I'm going to look at Andrew Lapierre's study. Again, we tested our boundaries, right? We came up with those optimums and said, well, maybe if we didn't do our math right, we could go up or down a standard deviation on all these amino acids and find out what is the sensitivity of the cow to these predictions, right? So we ran a study where we did that. We used our optimums. That was about 14.8. And we went down one standard deviation on all the essential amino acids. That would be our negative. And then we went up one standard deviation on all the amino acids, and that would be our positive diet. Fed them like all cows, good cows in a freestall. So it's all that noise in there too. I'm going to skip this in the interest. You guys will have the slides, but you can see the diets. You can see the crude protein levels, 14, 14, 7, and 16. We were cognizant of the fact that we didn't want a negative rumen nitrogen balance. So we made sure that there was enough rumen nitrogen to stay positive, so that didn't confound the data. This change in protein is really driven mostly by the change in amino acids and not in rumen nitrogen availability. All right, so here's our amino acids. Right, and you can see that our lysine, our methionine went from 69 to 88. Lysine went from 201 to 248. Histidine 60 to 87. Right, and arginine, we couldn't quite figure out how to get arginine to go higher down there, but we'll learn how to do that. It's all part of the process. Why am I showing you this? Well, again, it's back to the concept of how do the amino acids interact, right? Is it all milk volume? Is it milk protein? Is it milk fat? Is it energy corrected milk? Well, when we go negative and we don't have enough amino acids, we take a little hit on the true protein, but we also take a hit on the milk fat. And as we get closer to what we think the optimums are, we see the milk protein increase, but we always also see the milk fat increase. Right, and we can do the same thing as we go to the highest levels. Again, they're not significantly different, but we can see that we can move energy corrected milk. It's in this particular study, it's kind of a threshold effect. There's a numerical difference here, but it's not statistically significant. But the idea that as we increase those amino acids, we're not only seeing a protein effect, we are also seeing a fat effect. And that's what I wanted to point out to you with all of that, right? So I'm going to run out of time here, as I always do. So I'm going to go faster, but everything, if we're going to do components, we've got to focus on making sure the microbes are well taken care of, right? We've got to make adequate microbial protein. We've got to make enough VFAs. And that's the key to making this whole thing work. We need enough ammonia. We need iso acids. We need endogenous protein to allow all the bacteria to do their job effectively, right? I'm going to come back to some old data. And some of this goes back to Will Hoover years ago. Will Hoover, many years ago when I was very much a grad student, an early grad student, he would come around here and talk to us. and him and sniffing, and he'd say, hey, you know, we got to have sugar somewhere between 6 and 8% of the dry matter to optimize fiber digestion and microbial yield, and most likely to increase components, right? And they would come up with these tables of, hey, you need to have enough starch, but you need to have enough sugar, right? And maybe some fermentable fiber. And I think I agree with that. We probably need to make butyrate, right? And this is got this from Alex. You know, we talk about how do we put fatty acids together, and I'm always fascinated by this data because I think it clarifies how some of our diets should look, right? Because we get tied up in, well, palm versus oleic, steric, you know, where's the acetate? Well, the acetate's necessary for extension. What about butyrate, right? What do we do with butyrate? Well, I think this is fascinating because if you look at all these triacylglycerides and you look at them on a molar proportion for a triglyceride, and you know, if you look at the moles per 100 moles of fatty acid, the butyrate doesn't look very high, right? It looks like it's always mostly in the SN3 position. And again, it doesn't look like you need a lot, but it's also really small. So it doesn't take many moles to fill all this. But if you look at the top 3 triglycerides, right? Butyrate, 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 butyrate. There we go, all the way down, right? So when I look at this, I think to myself, yeah, acetate's important, but if we really want to make milk fat, we probably should be feeding a little more sugar. I know that's expensive in the US market, but somehow I think we need to try to hit those thresholds if we're going to increase it, right? I've had people ask me, how much sugar can you feed a cow? And I said, that's a good question. Here's some Irish pasture grass where they don't supplement a lot of starch. And if you look at the starch content of the grass, it's 2.2. And if you look at the sugar content of the grass, it's 24, right? It's just the opposite of what we would do. So how much can you feed? Well, you can feed about as much as you want if you can get it and it's cost effective, right? They don't have a requirement for starch or sugar, but the rumen sure likes to see one or the other of them. But I think, you know, this whole idea about how much sugar is an interesting idea because in pasture-based systems, that's the primary carbohydrate outside of NDF, okay? So more. So, and if we look at the relationship between de novo and milk protein, and Barbano and Malelli showed this quite a few years ago now, there's a strong correlation between milk protein percentage and de novo, right? So if we can do anything to enhance de novo fat, most of the time we're going to increase milk protein content, right? And I think this is really important. This is bulk tank data, but we're really starting to understand these relationships. I think some of that comes back to the integration with amino acids, right? And some of those other precursors that are necessary to do the de novo fat synthesis, right? And if you look at fatty acids, there's some data from Locke and McFadden's lab about insulin signaling and the right profile. And I think it's all about energetic efficiency. You know, Adam would say, don't overfeed it because the gland gets lazy. I think it's just saying, hey, I got this here and I don't have to make it. But if we look at altering the fat, you know, the palm to oleic ratio, which he did in this study by Jonas de Souza, you know, they've got quite a range here in the proportion of each fatty acid, 80-10 all the way down to 60-30. You know, so here's the grams all the way through. What I think is interesting is if you look at, and here's the composition of the diets in terms of their concentration of both of those. But if you look at the outcome, and I think this is interesting, you see because I always tell people I can move milk protein faster with fatty acids than I can with fatty acids. I can move fat with fatty acids, but I can move milk fat faster with amino acids than I can with amino acids. It's just the reverse of what you would think. So here's in this study, as they got the ratio of palm to oleic tied down, there was a 5.6 increase in protein yield as they achieved about a 1.5 to 1 ratio. What I found fascinating is there was about a 7% increase in lactose yield at the same ratio. And I think this is telling me that the cows were probably amino acid limiting because if there was enough limiting, if you overcame the amino acid limitations, you probably wouldn't see the carbon being partitioned to lactose. You'd see the carbon being partitioned to amino acids, and maybe some more milk fat. Right. So I think every time in a study like this where I see the lactose yield go up, it makes me wonder what might be limiting in other parts of the diet. Right. So I think, as I said earlier, I think cows have requirements for fatty acids like they do for amino acids. We just haven't figured it out. Looks like we feed a certain ratio of palm to oleic. The efficiency of use of absorbed nutrient increases. And in the 1.5 to 1 is for intake, right? And we can debate this, we can argue it. It's a starting point. Sometimes it's hard to do in the market with the high oleic beans. Now it's getting easier, and we're seeing responses to that. I'm going to skip this slide. I did this already. I'm going to get to some cows, right, where we did all of this. Most everybody's seen this, right? We did a rumensin titration at the request of Elanco because they wanted to do this on modern cows, and they wanted to test the effect of rumensin on milk fat. And again, this has nothing to do with what I just talked about, except that they allowed us to build at the time what we thought the best diet we possibly could build. All the things, not all the things, but most of the things I just talked about, right? The right fatty acid profiles, sugar, not too much starch, all the amino acids we talked about. And the cows were at 4.1 and 3.1 true protein, right? And this is in an abstract. We're working on the paper. Lysine, methionine were at the levels that we would suggest, 1.19 and 3.2 grams per mcal. Histidine was equal to the methionine, right? About 5% sugar, not a lot of starch. Pretty low fat levels, right? One of the things we've learned is don't overfeed fat. Get as much digestible NDF in there as possible. Right, cows consumed, they were about 71 to 72 mcals, 85 grams of methionine, and 229 grams of lysine. Right, where do we see the milk fat move? 4.6 to 4.7, milk true protein 3.35 up to almost 3.4. Right, so in established lactation, cows that were about 190 days in milk on average when we summarize this data, but managed to maintain milk yield through the big increase in days in milk, right? So the idea that we could move milk components in established lactation by meeting some of these requirements, and especially on the amino acid side, and see the milk fat response is consistent with that data I showed you from Lee. Right, in this follow-up study, this was we tested new rumen-protected methionine, 144 cows. Lysine was at 3.2 grams. Histidine was similar to 1.19 grams per mcal for all three treatments, and then we titrated in the methionine. In this particular study, we couldn't make the diet from scratch, so we had to work around a diet that was already being fed at the research farm, or else I think we could have seen a little bit more outcome. But if we look at this titration, right, they moved from 309 on protein to 324 to 334. But I think of greater interest here to this conversation, moved from 4.2 to 4.36 on fat. Like I said, and this was significant, if we could have made this diet from scratch, I would expect, I don't know about a higher protein response, but I'm pretty confident that we could have gotten a larger fat response if we had some other things in the diet. Okay. One comment, this also makes cows much more efficient, right? So if we think about efficiency, this amino acid balancing and diet balancing increased, we saw about a 4% increase in energetic efficiency. Overall nitrogen efficiency, if you're looking at what was partitioned to productive nitrogen and away from urinary nitrogen, there was an increase of just over 6%, right? So this is also good for the environment. Couple more herds here and then I'll be done. Northern New York, 3,700 cow herd, 90 plus pounds of milk in April. Right. So this is a herd we worked with the nutritionist for a few years off and on. It was hit and miss. And then finally we said, we're really going to do this. We're going to sample the milk correctly. But these are bulk tanks. We moved them from 4.2 to about 4.4 to 4.5 milk fat through everything that I talked about. And then they started feeding high oleic beans, and they went from about 4.4, 4.5 up to 4.68 and 4.77. And the true protein, right, it also increased in 2 jumps. It went from about 3.2 to 3.3, and then from 3.3 to 3.4 and almost 3.5 with the high oleic beans. So again, back to that fatty acid relationship with palm. We see this expressed when we get close to that relationship. Talked about early on the genetic capacity of cows. These guys have a herd of genomic Holsteins in their own barn, fed a similar type of diet. There at the same time were about 89 pounds of milk, greater than 5.2 fat, greater than 3.6 true protein, right? So about the future of cows, right? These guys are coming. They're in their first lactation. Can't wait to see what they're going to do as more mature cows. 2 herds, southern Pennsylvania. Again, same kind of thinking, fat in both herds before any dietary intervention was about 4.2. Protein was about 3.1. Got some of these concepts into the diet, amino acids, fatty acids, drop the fat, add some sugar. Got the cows up to 4.6, almost 4.8 on fat. Milk true protein at almost 3.5 in both herds, right? Not big herds. In established lactation, instituted the diets across both herds, right? So take home messages: insulin's involved in protein synthesis in the mammary gland for both milk protein and milk fat. You know, it's pretty obvious now. Amino acids have other roles that involve signaling and supporting the metabolism of other products such as milk, fat, and lactose. This is really cool. Fatty acids enzymes are inducible in sense supplies of nutrients, especially amino acids like lysine and histidine. I just said that. So to improve feed efficiency, formulating the correct amount of metabolizable essential amino acids relative to metabolizable energy is necessary, because part of that feed efficiency are milk components in general. And we've got to be a little more generous about how we look at this, right? And here's some steps just to optimize this. You guys are going to have these slides. I don't need to read through this. This is kind of what you guys already do. And there are some guidelines that we put together from a bunch of these studies. And you guys can take a look at that and give me feedback or ask questions. So Scott, I know I'm over a little bit. I'll take questions. Sorry about that.
Yeah, no worries, Mike. Before we get started answering questions submitted, though, we'd like to share a brief video. Then we'll be right back. Balchem has invested decades perfecting the art of nutrient encapsulation. And now, new AminoSure XL is setting a new standard, delivering 35% more metabolizable lysine than leading competitors. With AminoSure XL, you can provide your cows with a more consistent and higher quality source of metabolizable lysine, leading to improved and more dependable results. A recent meta-analysis found that feeding rumen-protected lysine led to an increase in milk fat percentage and 4.4 more pounds of energy-corrected milk. Feed new AminoSure XL to your cows and have confidence that you're using the most consistent, reliable, and cost-effective source of lysine on the market today. Learn more at balchem.com/XL. All right. As a reminder, you can still submit questions through the Q&A tab at the top of your screen. Mike, your first question is, the new NASEM was introduced just a few years ago, and you had presented some data showing that the genetics of dairy cattle are evolving rapidly. Is the current NASEM out of date, and how do we keep abreast of nutrient requirements?
Ooh. Is the new NASEM out of date? I don't know if it's out of date. Here's how I want to answer that. What was the rest? Would you ask me the rest of the question?
The rest was, how do we keep abreast of nutrient requirements for these genetically advanced animals?
That's a great question. That kind of haunts me right now. It haunts me and motivates me. Because now that I've given some of these talks, I've had people come up to me with this happens to me all the time. I get people come up to me after I say something like this. They come up and go, well, I got a herd that's 8.8 pounds of components. What do I do next? Right. And I'm like, that's a good question. I'd really like to see your cows and your diets and figure out what the potential is. I've got another guy who has cows making an incredible amount of milk, right, in the 200-pound range. And he says, Mike, I'm using your amino acid numbers. And every time I go there, I add a few more those amino acids. And he says, the cows always respond. Right. So I think the question's well placed. I don't think anything's out of date, so to speak. And I can't speak for the NASEM. I pay attention to it, but because of the time that I invest in the CNCPS, this is really where my head's at most of the time. I think the gram of metabolizable energy or metabolizable amino acid to energy is probably the safest thing to do right now. But until we get 7 out, there's a bunch of missing information, right? And NASEM they gave you 5 amino acids. I think those are important, right? They got the branch chains in there: lysine, histidine, methionine, isoleucine, leucine. I think we have to figure out at some point how to start paying attention to those branch chains, right? They're just very expensive. I had this conversation with a group of people this morning, right? I wish the folks who have chickens and pigs would figure out a demand for those things so we could get it out of a pharmaceutical grade, cost. Because I do, so my grad student, Alex, my co-author on this talk, Alex ran a study. We got really high productivity out of the cows. We just ran it through version 7. It says we're very deficient by like 20 grams deficient in leucine. Right. So, so there's always opportunities. The question is, if we see that, what do we do? How do we find that kind of leucine without overfeeding protein? I think that's going to be one of our struggles. So anyhow, I think there's a lot of opportunities. We just have to do the right kind of research to figure these cows out.
All right, very well. The next question: what should be our target metabolizable amino acids to ME ratio be for fresh cows the first 21 days to 30 days in milk?
That's a good question. I'm going to stick with what I just gave you. So we did, and I'd have to go back and look at the numbers to make sure that I've got this correct, because I can't keep the whole thing. But if you look at the data from Trent Westhoff, that would be the study that would give us some sense of direction there. And I always forget this number. I think it's between, and I'm not going to do this on a gram of amino acid basis. I'm doing it on an MP basis, but it's higher than 53 grams per mcal of ME, and it might be 58 grams of MP per mcal of ME. And that points us in the direction, and then just tie your amino acids to the same relationship. Okay. Right. So you can back your way into it that way. And in that study, they got a nice response in milk yield, like 6 kilos, 7 kilos.
Next question is from George: does slug feeding grain in the robotic milker have an opportunity to increase components, or just ECM in general?
Well, I think being able to provide more nutrients in the robot could be a way to do this. When I hear the word slug feeding, that scares me a little bit, because now I think about acidosis. That's probably not what George meant, but I think the ability to use the robot to titrate in some of these limiting nutrients is probably an interesting way to do it. And I'm not sure that everybody.
Mike froze. We'll give him a few moments. So I think we'll move on. I will tell you this is that we're preparing to record a podcast with Dr. Van Amburgh. And so any questions that are submitted that have gone unanswered, we'll certainly make sure that those get answered during the upcoming podcast. So with that, I want to thank Dr. Van Amburgh and thank everyone for attending today's webinar. If you have additional questions, please submit them to anh.marketing@balchem.com. The Real Science lecture series continues with educational topics each month, including our next one, which is on December 3rd, titled Global Dairy Market, Where It's Been and Where It's Going, and that'll be with Mary Ledman from Rabobank. We'll also be hosting a custom webinar with Dr. Clay Zerman, and that one's titled The Real Story of AminoSure XL Precision Release Lysine. Now, Balchem launched a new rumen-protected lysine product last month at the new, Cornell Nutrition Conference, and this webinar will review the supporting data behind that product. Visit balchem.com/realscience for details on future webinars and to register for upcoming events. Balchem's podcast series continues to offer a deeper dive into our webinar topics. Log on to your favorite podcast platform and search for Real Science Exchange, or visit balchem.com/podcast. If you want a really cool Real Science Exchange t-shirt, just subscribe to the Real Science Exchange. Send us a screenshot along with your address and shirt size to anh.marketing@balchem.com, and we'll get that off to you right away. On behalf of Balchem and Dr. Van Amburgh, thank you for joining us today.